I don't know if you couldn't
All right. So,
I couldn't write the first one without sounding like a lunatic. I didn't understand which sister was which.
first thing I want to mention, anybody got homework to turn in to me?
I have a question.
A couple of you emailed it to me, that's fine. A couple of you did it on Classroom, that's fine. Easiest for me is for you to hand it in class, because then I put it in my folder and I make sure, but either way, it don't matter. Any homeworks for me that I can take now? I have a couple that I can hand back at least.
I'll say, if it's acceptable, I was wondering if I could get some help during dish.
Yeah, absolutely.
No, it's not.
Joey.
not.
Both of them.
Aiden, like, ask.
Just John on their own.
Don't make me whip that. Don't make me rip.
Yeah,
Getting help in here.
Oh, I got my money.
Aiden, you got one for
Don't
me?
make me rip your weave off. Okay.
You got you. Again, I want to remind you guys, please don't be neglecting
know what you just said.
your homework.
Don't make me rip.
I'm not. They're based. They should be free points, right? I'm giving you points to study, right? I want you to be studying. You need to be studying as we get ready. So each unit, I'm going to have, again, that workbook. You go in, pick out 10 questions that you want to try. I really encourage you to do the problem and grade yourself. I would love to see your work in pencil and then your corrections in pen. I don't care if they're right or wrong, but I want to see that you're checking your own work, and if you got one wrong, try to figure out what you did wrong. Now, I'd love to see you write out, like, use the wrong equation or solve it correctly. You don't have to, but I want to see you do the work and then grade yourself so I can see, okay, they're taking the time to check if they got it, not just willy-nilly doing some problems.
Where
And
did you say the answer key was?
it's
Because
be careful with, I know where you're going, but whatever you're going to do, make sure it's useful to you.
no, but I thought you said you posted an answer key for us to check our work, didn't you?
Yes.
Okay,
So,
I did not see the.
yeah,
Maybe I just absolutely missed it or what?
It's in the workbook. It's,
It is?
yes,
Okay.
it's at the bottom. So,
I
like,
kept looking and looking. I guess I didn't scroll down far enough.
yeah, so, like, if I'm looking at,
It explains why it's like 3,000 pages long.
yeah, they're long. Don't get overwhelmed by that.
I get overwhelmed.
Where did I...
It's part of my situation.
So we're talking like Unit 3, right? So if you open up the workbook, I post them each day. So Unit 3... Oh, wait, these are going to be the FRQ.
I think one FRQ should be equivalent to 5 multiple choice questions. So if you assign 10 questions and you do 5 multiple choice and FRQ, that's equivalent.
I have a better chance of multiple choice.
I'm for that.
Okay. I was just saying because like most of the FRQs, not saying I'm gonna do an FRQ, but I'm just saying that theoretically, like an FRQ has multiple steps to like multiple points. So it should be worth more than just one question.
Okay, wait a minute. So the workbook is...
Oh no, I guess we can't do any questions.
I guess we just better go take recess.
Recess.
Just for Unicell, Unicell.
We'll go hit up Sophie's. Oh wait, we don't know if I'm talking to recess.
Can you go to item, please?
Okay.
Yeah, so here's the Unit 4 workbook.
I'll feel like paper gas.
You can skip this.
Thanks. Well, technically, if we just took both of our trucks, we can fit everyone in this.
That is true.
Collectively. Not legally.
I
but
mean, I've
collectively.
got 4 extra seats and a hatch.
You want to pull
Down?
something in?
We're going to items.
Right, we got a smaller
We're just gonna
class.
leave. We can take it right now.
Need a sprinter bus. That's what we need.
Plus Maggie.
I know. Let's go tomorrow instead of doing the mock exam.
No, we need the bus that Mike Scott used for his paper.
We can do it. Shoot.
The
Take one of the mini ones. You're right.
Jack
It's
is
14. I
one.
think it says.
It's 14.
Church is great.
In
And we
Chinese.
can talk about the physics of ice cream.
Yeah, exactly.
Yeah, we could talk about the
See,
complicated
this is one
process
thing
of
that I
freezing
like
ice.
about
Where-
the process, that you can essentially
Now I'm confused. Where?
anything.
Because I'm double checking in the workbooks that I'm posting. They might have been only the. I thought I posted the answers
I
too.
didn't see the answers, but I just wanted to make sure I wasn't the only one that just didn't see something. Because I don't see things all the time.
We'll just go get an ice cream. We'll figure this out in like 6 to 8 months.
We'll figure it out in 2 months because I won't care.
Is this unit 2? Right, yeah, it's right there, those are the solutions.
Yeah, there we go. Okay.
Oh, okay, now I'm
So they're section by section. Yeah, I was gonna say they have them, but I just.
It's kind of stupid, the way they formatted it is.
I agree. It should come like it should be multiple choice, then multiple choice answers, but they.
Like, throw like 50 questions, then do like the solutions to the 50 questions all at once.
How about we talk about the physics of a profit?
Where is your brain?
Yeah,
We don't have a brain.
It's somewhere. It's just not here. Yeah. So your unit 4. Here's your answers to the multiple choice. So they're in the workbooks. So when I tell you, okay, we're reviewing unit 4, I tell you, okay, take 10 multiple choice from the unit 4 workbook, right? Do them and then come here and find the answer. And they actually do a nice job of giving you the equations and things. So this is why I'm telling you I want to see these corrections. I want you to show me that, okay, like you figured out what you did wrong. That way I know you learned something. That's the goal. Yes, I want you to do it yourself. Try, practice. Then grade yourself and correct your mistakes. So you know, oh, that's how I do it.
What about the questions when it simply just wants you to like find something? Because like one of the questions was talking like an ant on a flywheel, which is such a weird question, but
Yeah.
whatever. And it is asking like different points and it has like I, and IV.
So you just pick like which
so
one?
I just wrote the letter down.
Yeah, in that case,
But I didn't
maybe
know, like,
the answer key has a description of like it's this answer because of conservation of momentum, so you could jot that down. I get what you're saying. You can just put the answer. The goal is, okay, when I look at your paper, can I tell that, okay, Josh did the work and then tried to correct his answers and figure out what he did wrong. That's what I want to see. And again, I'm not going to critique you that much. I'm trying to give you some free points in the class for you doing your review as we go unit by unit. Okay? So enough of that. Today I want to, again, we're on unit 4. Right? We're trying to do one unit a day to kind of get our minds back on it. So unit 4 is all about energy. So I want to go through that quick. So I want to do a practice of that, and then I want to try to end early so I can let you ask me questions or
Watch that video.
I thought I showed you that. I found it right at the end.
Yeah, but then the bell already rang.
Oh, well, sorry. But yeah, he was, like Brody mentioned, that what do they call it, like gravity ride or something, and he's like leaning forward. It's pretty sketchy, but anyway, unit 4 was all about energy. That was the big idea. But energy has a lot of parts. There's different forms of energy. There's kinetic energy, potential energy, elastic potential energy. Work is another part of the energy unit. Right? When you do work, you're changing the energy. And then we also talked about power. So quick review. Did anybody remember quick equation definition of what work is?
Oh, it's force over time.
Force is part of it. Force over time is... No, that's force times time.
I thought it was like work. No, I said what is work?
Yeah, the equation for work. How do I do work in physics?
Force times distance.
Bingo.
Okay,
Good memory. Right? Again, I don't necessarily expect... You don't have to have that memorized. I'm almost positive that's on your equation sheet.
Yeah. I found the video I was talking about yesterday.
The gravity spin one?
Yeah.
Can you hold it till we have work time? But yes, I want to see it because I'm curious. Force times distance. In physics, when we say work, I'm not talking about you go to Walmart and you work, or you go to McDonald's and do... That's not physics work. Work in physics is specifically when you apply a force, and that force causes a change in distance.
Right, because it's possible to have no words even though you put that.
Exactly, right? I could push on a brick wall as hard and as long as I want, but if it does not move, no work. Okay?
I don't know where to find it.
I think they have presentations next door. All right? Units.
Good job.
Units of force. How do we measure force? Newtons. How do we measure distance? Meters. Very good. So what are the units of work? Newton meters. Bingo. Now if you take what a Newton is and what a meter is and combine them, you get a joule. Joule should ring a bell with the idea of energy. We always measure energy in joules. Work is energy. When I do work on an object, I'm giving it energy, or I'm taking energy away. They're related to each other. That's why we learn about work in the energy unit. Okay? So you got classic example, the dude's mowing his lawn. Right? He's pushing that lawnmower forward, and he's pushing on the handle.
Ooh, that looks like the Pixar lamp.
The who?
It looks like the Pixar lamp.
Kind of does.
This hat is shaking his head.
The lamp.
Doesn't he? And how he has his head turned? He looks
I
like a
guess.
Pixar lamp.
Anyway,
The two down, one down.
force.
And then was the
The force is at a weird angle. I'm wanting to know how much work he does along the ground. So I need to know how much force is acting in this direction. How do I do that?
Split the force.
You break it up. You can split any force at any angle into a y component and an x component. These are imaginary forces. They don't actually exist. You're taking the actual force and breaking it into its basic parts that, when you combine them, create the actual force. The reason we do this is because if we figure out what part of the force acts this direction, well then our work equation's easy. Force times distance. Force, distance, done.
That's all the people in the background. They get pulled in.
Yeah.
No, that's the symbol for like group discussion, talk about it.
Oh, I just see all these people
It's not
sitting
just like, oh, take notes on this. No,
back,
it's
sitting
a
back
problem.
on the tree line watching this dude mow.
Do you guys remember this part? This is a slightly different form of the equation.
As a matter of fact, I do not.
If you didn't take the force and break it into two parts, that's okay. You could use the full version of the work equation.
No.
This cosine of the angle, it's breaking the force into a certain part for you. So you could do this first and find the x component of force multiplied by the x distance, and you're done. Or you could just use the full equation. This is my force. It's acting in this direction, and the cosine of theta is the cosine of whatever angle my force is to the direction I'm interested in. Well, they're 51 degrees apart from each other, so I do cosine 51. Either one. When I do this, at first I broke the force up. It made more sense to break the force up, then plug it in the equation. After I got comfortable with it, this equation made sense, so I can go straight to the full equation. And I'm almost positive that the full equation is listed in your equation sheet. I want to confirm if that's true or not before I...
It is.
Where is it at? I can't...
That whole thing. Is,
Oh, yes. Yeah, this whole thing is straight from the equation sheet. It's right kind of upper middle part. Work is force times distance if the force and distance are in the same direction. Otherwise, you can do force, distance, cosine theta.
What are those two lines right after this?
Parallel. If
Okay.
force and distance are parallel to each other, right,
Okay.
then you just do force times distance.
Okay.
I think I'll just
Easy.
Really?
Easy as a summer.
You wanted to
Easy as it's gonna?
She wanted a donut.
No, I got 2 donuts.
Dang.
I heard that you didn't like answer your FFQ or something.
No, I did. Some of it.
We were wondering if you had 2 AP mock exams today.
No.
That would have
My
been
mocks-
horrible.
My mocks aren't together, but my actual exams, I have 3 2-days. Or 2 2-days.
So you have 2 tests and then 2 tests? Oh my
In
goodness.
2 days. I think it's
That's
a 2-day
awful.
span, I have 4 tests.
And AP Physics is one of them?
I think so.
Oh,
And then there's
I do
one-
not envy you.
And then there's one next week. And that's it.
Man.
I'm pretty sure, but I think Maggie
She might get so mad.
Yeah.
So Maggie, you didn't miss a ton. We just got started reviewing for Unit 4. Unit 4 is energy. The first part was work. Work is force times distance. The full equation, guys, are you with me? I hear a lot of side chatter. I'm trying to review this for you guys, get it all back on your minds. I know, that's all right. So force times distance, cosine theta. Josh, you asked what's this symbol? That means parallel. If the force and distance are in the same direction, just multiply them.
So theoretically, if he was just like not pushing on the handle and just pushing out the bottom of the mower,
Yes.
it would be like considered parallel.
Yes, it would be that force he's pushing times the distance that he moves it, done. This also can be used. What happens if the lawnmower is moving this way, but he's pushing this way? What do you do then?
They're still fair.
They're still parallel. Am I doing positive work? You're doing negative work. If I'm applying a force on an object in the opposite direction that it's moving, I'm not giving it energy. I'm not adding energy. I'm removing energy. Now, if you didn't remember that, use this. What's the angle between this distance and that force? What's this angle? 180.
Is it not?
Anybody know what cosine of 180 is? -1. It adds it for you.
Is it not negative energy or negative work if like you're like you said the brick wall thing? If you're pushing on a wall and it moves, it would just be zero, nothing.
It's 0. Why?
Because
There's no distance.
okay, no, okay.
Right? If this is 0, I don't care what the force is. It could be 50 billion newtons. 50 billion times 0 is still 0.
Okay.
That's really important to remember. Work, you need force and you need distance. You could do positive work that increases the energy of the object, or you could do negative work that takes energy away. This is also important to remember. The total change of energy in an object is equal to how much work was done on the object.
I want to make a game simulation where everything is negative until you push something.
I don't know if that would work.
Because inverted control.
No, so like you just
Like take an equation and flip everything back.
Yeah.
Like
and so like
that'd
when you
be-
go to something and you try to push it.
that'd be an interesting thought experiment to look at. But let's pause on that. Okay?
Yeah.
Guys, I need your attention right here. 2 people are going to run up. I don't know what this is, to be honest.
Is that the guy from Little Caesars?
It looks just like him. Especially this one.
Except in America, it's the Mayan. I think it's the Mayan.
Chichen Itza?
That might be it.
Chichen Itza. I'm pretty sure that's what it is.
Yeah, one of those.
Regardless. These 2 people, they are going to race up this tower.
Their pizza
Watch
delivery
it.
delivering to the Mayan god.
Who does more work? Who did more work? Be careful. Think this through.
Same.
I think Little Caesars did.
The same.
Guy on the left.
Correct answer is Pizza Hut. No one else Pizza Hut.
Who did more work? Watch it one more time.
It would be the guy on the left because he's actually accelerating, and that dude's kind of just like staying at a constant speed.
They're identical. They're twins. Same mass,
What is
same height, same everything.
I think it's the guy on the left.
Let's think back. Work. What is work equal to?
4 times distance.
Okay, so distance. Are the distances different?
Distance
It's like the same.
Distance is the same in both cases.
But
If they are the same, if they're identical twins, which one needs more force to go up that object?
the guy in the red.
Huh?
The guy in the red because he was behind and he was faster than the other one. Therefore, you would have to apply more force.
Do they need
At
the
a
same?
specific time, yes, but we're looking at the whole motion.
The same. Would it be the same?
They're the same.
Even though the guy on the left got there before him.
Yes.
It's
Okay.
still the same distance. And
That was the only thing that I
Yes,
wasn't quite sure
And
about.
and you made a great point, Aiden.
But you're
And
still wrong.
Andre, you said that too, right? This guy on the left, he was accelerating. Newton's second law says F equals ma. Aiden, calm down, all right? F equals ma means if I accelerate more, I need more force. And you guys are exactly right. However, when you look at total work done, you can't just look at the force at this point. Because, right, he's accelerating, but then he's at a constant speed. Sure, this force is big at the beginning, but then your force, I don't know if it would go to 0, but your average force would actually be the same in both cases. So, however, what did you guys notice was different about the work that they did?
I might have that too.
They did the same work. What was the difference between their two routes up the stairs? Speed. Right? And this guy got there first. It took him less time. I'm mentioning that because power, we talked about power.
Is it work over time?
Power was work over time. Right? Those two people did the same amount of work,
Different path.
but who needed more power? The guy on the left. He went up faster. He did the same work in less time. So power is work over time. What are the units of power?
No.
That's units of work.
Oh,
That's okay. That's part of it. What's time measured in? Seconds. That's our base unit. Joules per second is the units of power.
Wait, then what's watts? Because John said watts, and I actually come back to it.
It's this. This is you're getting
Oh, so you were right.
Very good. Very good.
I told you I was right.
Watts is a different unit
10%
that basically instead of saying joules per second, they created their own unit, watts, to measure power. Watts, 1 watt is a joule per
It's
second.
like
So this is the base, the original unit, and then this is a unit that we made to simplify. Like we can talk about power with just one unit.
But watt is the last name, so essentially God was like, I don't like that unit, I'm going to make it my last name and create my own unit.
Not quite. He discovered it, so he gets the right to attach his
He
name.
discovered that his last name is
No, he made it.
He made
Like he discovered what a
He
joule per
discovered-
second. He discovered power,
he
and
discovered the joules. Okay, because
he
I heard
quantified it, described it, showed it.
Because Jules is also another person's last name, so I thought.
I think it is.
So I thought that like Jules was the first dude, and then Watt just came around and was like, no, you changed it to my last name.
Well, he discovered the relationship and described
Okay.
what power is, so then he gets the right. And I think it talks about that briefly. James Watt. He was the guy that also came up with a horsepower. Right? We measure cars in horsepower. That's our American unit of power. Now, you might see power in your problems, but we don't like to use horsepower in physics. We want to convert it to watts because we want those SI units. What he found was a horse could lift 550 pounds for 1 foot. That's work. In 1 second. Work over time, there's your power.
1 horsepower is 550 pounds.
No.
It's moving 1 foot.
1 horsepower is the ability to move 550 pounds for 1 foot within 1 second. Horses
I
are
don't think about like a horse could weigh like 1,000 pounds or like.
horses are
15
very
pounds.
powerful animals.
So if all they're doing is they're just pulling a third of their body weight.
Yeah, it's
If
a
it's
scale
a-
thing.
yeah.
But regardless, this was his way he tried to measure. He used the horse to measure, and this is an arbitrary unit. But this unit we use to compare.
Because horses were around first.
Do you guys know average human horsepower? If we measured our physical power, how many horsepower would we have?
It depends on the person
No.
now.
2.
It's teeny.
Yeah, so
Wouldn't it
I think
depend
it's
on the
less than
person?
half.
Well, it depends on what you're doing.
It doesn't depend on the person.
Well, yeah.
The person's abilities, yes.
Okay,
Some
because-
people are more
because-
powerful than others.
Because what I can move and what Brody can move would be two different things.
Actually,
But it's also based on your weight.
it doesn't matter who can move more. Time is the critical
Okay.
factor of power. Now, it would
But if I
depend,
can't move it at all and Brody can move it,
Good. That's
no matter
true.
how slow it goes.
but you can't just look at what could I do, what could Brody do. The time is important, right? Humans, like my ICP classes, they literally ran upstairs in the bleachers in the gym and measured, right? I did this much work and I timed myself. They were roughly like anywhere from 0.3, some of them were like 0.7 horsepower. For reference, Usain Bolt, his world record setting 100-meter dash, the power he used to complete that world record setting race was like 3.5 horsepower. So stop and think about that. We have weed whackers and lawnmowers that are more powerful than one of the best athletes in the world. So kind of use that to, one, limit human physical ability. We aren't as amazing and strong as we think we are, at least looking at a physics analysis. However,
We're smart enough to figure it out.
we make cars that have 1,000 horsepower in them. Can you imagine having a car that you have to strap 1,000 horses to be able to do what it does? And we have it in this little chunk of metal? That's amazing. It's really cool. That's engineering is really, really cool.
Sounds like an extreme sport that I was watching.
Speaking of horses, you can use power to figure out, okay, a horse, average of 1 horsepower, which is 550 pounds for over 1 feet in a single second. So the question is, if this horse is trying to pull the plow, and the plow resists with 180 pounds, so that means the horse has to apply 180 pounds of force, how fast could the average horse pull the plow? Well, you might be thinking, wait a minute, how fast? That's speed. I don't have speed in my equation for power.
Feet per second.
What?
Feet per second.
If I did distance per time, that is what speed is. The definition of speed is how far do you move in how much time. So, come on. That's a great point, Ethan. You can have a different equation for power by recognizing this is speed. So force times velocity. If I know how fast something is moving and how much force it's exerting, that could tell me the power. So then you do your equation. Horse's power is 550. The force it's pulling is 180. It's simple algebra. 3.1 feet per second. That horse could move that plow 3.1 feet every second with its power. That's what it could do. Ethan?
I have a question about like the Usain Bolt thing.
Okay.
So there's absolutely no way Usain Bolt's able to move 550 pounds. So how does he have 3 horsepower?
Good question. Power is force, distance, time.
Yeah.
Okay? Oh, how do I want to say this? Oh, let's use the force velocity version of the equation. Let's say Usain Bolt, his record-setting race, what did he do? 100-meter dash in what, like 9 seconds?
Yeah.
Let's approximate it as 10 seconds. So what's 100 meters in 10 seconds equal to?
10 meters.
10 meters per second. Power equals force times velocity. So if his power was, let's say, 3 horsepower, oh, this isn't going to work. We're going to use a metric version. Let's say he used, how much force would it need to propel himself at that speed? We'll just make something up. It doesn't matter. I'm just using this as an example. Let's say 100 newtons. 100 newtons, what's 100 times 10?
1,000.
1,000 joules. Right? That's the power he used. Right? That's what actually happened. What happens if I run the race? Imagine I have the same power as Usain Bolt. I do not. At least I don't think so. But I walk. I'm going to walk. I'm going to walk with 10 newtons of force. Right? It's really easy. I'm just going to walk. It's not hard. I don't have to use a lot of force.
Same boat probably.
Do I finish that race at the same speed?
No.
10 times what equals 100? Wait a minute. I did this backwards. I'm going slower. Right?
You put in 1,000.
Wait, why isn't that making sense?
10 newtons. 10 newtons.
Oh, I'm assuming that I have the same power as Usain Bolt, which isn't fitting my example for you.
Are you telling us you don't have the same power as Usain Bolt?
Probably not.
I feel like
Exactly.
What is real?
I want a refund.
what if the refund all the time is same stuff?
So you just do like, you have 50, you put in half the work
90 days.
and finished in
And only 30 minutes.
over half the time.
I'll be a judge.
I'm confusing myself.
By the end of the year, we spend 135 hours.
I go to
Once you're 8, and then it's twice that. It's a dish.
Oh, shoot.
I haven't been here for Ish for like the past 2 weeks, honestly.
So if you stay here, rated in dish, then you would.
This is a bad example because the time isn't explicit here. So it's not making sense.
They make the time explicit. Here,
You know, just make it up.
Yeah, so let's do 100 newtons for how long? 100 meters
For 10 seconds.
in 10 seconds. That would give us 1,000.
Because we already did that.
Okay? So now, what happens if Usain Bolt, same force, same distance. I shouldn't have filled this in. That was my mistake. Same force, same distance, but he's going slow,
So it takes
longer. Say it takes him twice as long. Now what do we get? This is 10,000 divided by 20. $500. So do you see that? If it takes longer, you don't use as much power.
Right.
So I forget what your original question was. There's no way he has that much horsepower?
How
Yeah,
can
'cause
he have
A horse is moving 550 pounds, and you say Bolt can't move 550 pounds.
Yes. This is not a rigid definition. This means that any combination of distance, force, and time would equal 550, in this case, horsepower.
Gotcha.
So that one horse could do half of the force. Maybe it's only 225 pounds over twice the distance in the same amount of time.
Okay.
It's
yeah,
easier to pull that force, but you have to move it longer.
But it's still the same
Right.
number of horsepower.
Exactly.
So that's why you can have like a car and say it has like 1,000 horsepower and it can go like stupid fast. And you
Yep.
have, like a tractor that has like 500 horsepower and it can still pull that car backwards.
Yeah, well, that has to do with torque.
Yes, but I'm saying like the same thing. I'm like it can have half the horsepower, but it's like,
Yeah, and that example pulls in other concepts.
Oh,
But-
so like Usain Bolt is only moving like a couple hundred pounds of him,
Yeah,
but he's moving it really, really, really fast.
Very quickly, yes.
Okay.
That is why he has a lot of power. Right? I could do the same amount of power by pulling maybe I combine these and say I pull 1,000 newtons, 1 meter in 10 seconds. I only have to go 1 meter,
Right.
but I'm doing the same work in total, but less or the same time. It's any combination of those variables. I apologize for
Gotcha.
missing my mistake at the beginning. Okay? So I want to shift gears. That was all about work and power. Work and power change energy of a system. When you do work, you're changing the energy. 100 joules of positive work adds 100 joules of energy. Energy can change forms. Right? If I drop this ball, what kind of energy does it have right now?
Potential.
Potential.
Gravitational.
Gravitational potential energy is, if it's off of the ground, gravity has the potential to start moving it. What happens when I drop it?
Start turning into kinetic energy.
All that potential energy is released and gives it motion energy, which is kinetic energy. Physics class, energy. Jeez. Sorry. Butterfingers. I'll put that one down. In physics, when we talk about energy, we're all about, okay, what energy does it start with? How does the energy change? Right? The work is changing energy. Positive work increases energy. Force and distance, if they're opposite, I'm taking energy away. In physics, when we say mechanical energy, we're mechanics, motion, that's what we're looking at. I don't really look at thermal energy or chemical energy or nuclear energy. I want to know the energy of my position in motion. Well, that comes down to potential energy, the energy of height, essentially, and then kinetic, the energy of the actual motion itself. Potential energy you could think of as the energy of its position or height. Kinetic energy is the energy of its motion. So now here's another example. I want to know, how fast am I going to be going at the bottom of this massive roller coaster hill?
Pretty fast.
Pretty fast is a good answer. We have the maximum height at the peak. We also have, I think that's all we need to know. So at the very tippy top, what kind of energy do I got?
A lot of potential.
Lot of potential. You got to imagine, right, the chain brings you up there, and then you pause temporarily, and then you start going. So if I've paused briefly right here, how much kinetic do I have?
No.
0. I am starting with all potential energy. I've got a lot of it, but that's all I have, because I'm not moving. Well, wait a minute. When I come all the way down here, I'm back on ground level. Do I have any potential energy when I'm on the ground? No. So where did all this energy go?
It's not kinetic.
It's now kinetic.
You move.
All this energy got converted into motion. So I'm flying at the bottom of this hill. That's how roller coasters work. They lift you up. That engine, right, the little motor, the chain drive, has to do work on you. It gives you energy, and then you release all this energy, and it sends you into motion. We can calculate that. You guys remember this? MGH?
Aaron General Hospital.
There you go. Potential energy due to gravity is Marion General Hospital, MGH. Maybe that'll help one of you on the test.
I don't, but if you don't know what the M and the G and the H is, then
It's on your equation sheet.
That's gravity.
It's mg delta y, which is change in y position. Height is going from 0 meters up to your height. So this is why MGH is a little more straightforward. That's how you calculate potential energy. Kinetic energy is 1/2 mv squared. 1/2 mv squared. I've heard that so much that that's what I think of. I say it to myself in my head. If you don't remember it, it is, yes, Yeah, so kind of, again, upper middle. K equals 1/2 mv
Okay, hold on,
squared.
how many down is it?
It's the 9th one down. It's all right. You have this equation sheet. If you don't memorize it, that's fine. If you do, that's easy, right? But you don't need to. Well then, look at this. Mass cancels out on both sides. I don't even need to know the mass of the car. Right? It doesn't matter. It cancels out on both sides. Bring the 2 over. Gravity, I know. Height, I know. And then I literally just solve for velocity. 96 mile an hour.
Oh my goodness.
Kind of makes sense if you look at how... These are buses. In case you can't see that, these are buses. Right?
Straight bus.
100 meters, or 93, 300 feet, that's a football field up.
That's like at least 2 buses.
Right? Is that...
No.
100 yards, isn't there roughly 3 feet to your yard?
Roughly 3 feet to a yard. Roughly 3 feet.
Right, but the playing field, right? You always say 100 yards. So roughly 1 football field up. That's pretty high up. You got a lot of energy. If you release all of it, makes sense that you're moving 95 mile an hour.
The dragster is bigger and it goes faster.
Huh?
Taller and it goes faster. The top of the dragster.
Top of the drag.
420 miles. No, it's up. Sorry.
NHRA?
117 miles an hour. Something like 120 miles an hour. I think.
As 11
420 feet high.
420 feet high, you go straight up and then straight down.
Wait, what is this? Is this a ride?
Yeah.
Yeah, it's in Cedar Point.
Yeah, it's called the Top Thrill Dragster.
Top Thrill Dragster?
Top
Yeah.
of the dragster.
It shoots you up 420 feet,
Oh
And then
my
you just drop
god.
straight back
and you
down.
just drop straight down. So like.
So you go up and then down?
Straight down.
Oh,
And the start
Ugh.
it just
It lasts-
launches you.
It literally lasts like 17 seconds.
oh, I would get sick doing
And
that.
like, it's not like slow up and down. It launches you at the start, 120 miles an hour, and you go up.
Well,
and
you
down.
Oh
just
my
just
gosh.
launch at 120.
Well,
That's crazy.
But yeah, you just shoot straight up, and then they have to stop at like every 30 minutes or whatever to check the brakes.
Okay, well, good. Okay, let's pause that. I want to get through this. Alright, so if you're looking at skier on the slopes, I'm going to ask you, hey, how much friction is acting as you ski down the slope? You're like, I don't know. Well, use energy. You know the mass, right? This guy is 78 kilograms.
So I thought we were.
You could measure, okay, he starts here, ends here. The vertical height is 17.5 meters. The actual length of the slope, 25.7.
You just stopped in the middle of the hill.
He's right there.
No, this is a picture of what's happening.
You said he stops at that point, right?
Good
He
grief.
stops in the middle of the hill.
This is why we can't get stuff done. You guys keep distracting and hypotheticals.
No, because
Good grief.
We're trying to be observant.
But of completely irrelevant things. Yes, I understand he's...
What do you be concerned if a guy just really stops in the middle of the hill?
Do you think photographs, the person is actually frozen?
And who took the photograph? Was it the cult that we saw from earlier?
Oh, for goodness
Yeah, they're
sake.
watching him too.
Can we please stop? Let me get through this. In your work time, you can waste it if you want. I don't like that, but here's the length. Obviously, you start, say, the top of the hill, you're paused, and then you start going down. At the end, you're up to 18.2. So the question again was, how much friction acts? Well, look at this. You could figure out the potential energy, right? I had a lot of potential energy, and I released it all. Let's assume that this was ground zero, right? Mass, gravity, height. Here's the height. That tells me how much potential energy I start with. It's 0 meters per second. There's no kinetic energy. Well, at the end, I definitely have kinetic energy. I could find that. 1/2 mv squared. Here's the mass, here's the speed. Boom. What I'm missing, and what you would see, is these numbers don't add up. Well, you're like, where'd the energy go?
Friction.
Yeah, friction. You lost energy. Friction took it away from you. You knew friction acted during the entire motion along that hill, which was this distance. You just have an equation and you figure out, oh, friction was 17.8 newtons. That's the average force that friction resisted your motion. Again, this work should be over here. You always do initial energy plus work. If work is positive, it's positive. If work is negative, you add it to the other side. That's why this over here should be negative, because you lost energy from what you started with. Hooke's law, this should ring a bell. The force of a spring is however much you move it times how stiff it is. Right? Well, if you plot force and distance, guess what? Force times distance is work. So if you're given a graph, the area underneath force distance graph is your work. Now this is a triangle, so I would take force times distance, but that's one big box. My graph isn't a big box. It's cut in half. 1/2 base times height. That's the area of the triangle. That's also the equation for the work of a spring. I don't know if this one's on here. It is. It's the second from the bottom on the left. If you want to know the energy in a compressed spring, there it is. This one I want to talk about because this is kind of applicable. Right? When you drive your car, you're moving at a certain speed. When you hit the brakes, you come to a stop. Well, if you're thinking about conservation of energy, you should ask yourself, wait a minute, I had a bunch of energy and now it's gone. That doesn't work. That doesn't happen in physics. So where did the energy go? You removed it from the car by doing work. So if you look at, okay, you can do some crime scene investigation. I got skid marks that lasted 18 meters. I know the coefficient of friction between a tire and the ground. All the energy that I had equals all the work done that pulled the energy away from my car. Right? Well, do you guys remember the equation for friction? We've done friction multiple times.
Friction is the thing I remember.
Yeah, because I remember in a lot of stuff we did, it was friction was considered negligible. So I
True.
don't remember anything about it.
We do have it's one of your equations.
What unit? I mean, what?
Look at the fifth equation down. I don't know if anybody has them, but
What chapter did we learn about that?
we learned about it multiple times throughout. Like dynamics, we learned about it. Here we learned about it. Friction is equal to the normal force, how much the car presses into the ground, multiplied by the coefficient. How grippy are two things? If they're really grippy, this is a big number. 0.92, that's between rubber and asphalt. Those things are very grippy. That's why we make tires out of rubber, or at least one of the reasons. So force of friction is these two. I plug them in here. What is the normal force equal to of a car on the ground? Normal force is how much the road pushes back up. What does the normal force balance out?
Gravity.
Gravity. Gravity is mg. I got mass, so I can eliminate those from my equation. Rearrange a little bit. I know this, I know this, I know this. Just leaves one unknown. That's algebra. So, right, someone that's doing CSI, they could actually figure out, yeah, this car is going about 40 miles an hour. Right? So you can kind of get a picture of what's going on. This one, I don't want you to pay attention to the derivation. I want you to take note of this. We talked about potential energy here on Earth, mgh. You could also talk about potential energy of two objects in outer space. That's U capital G. And it's equal to, again, this is part of universal gravitation. I want you to point out or notice that it's negative. I'll talk about that in a sec. I think that's all I wanted to talk about. Oh, here's an example of why the potential energy of universal gravity is negative. If I go from the final position is here and the initial position is here, I subtract these two. Negative 6,000 means when I went here to here, I lost potential energy. That's why it's negative. It's just a little weird. Remember those big ideas for each unit? Some of these we've already done. Work is force times distance, or force distance cosine theta. Same direction creates positive work. If I push in the direction that it goes, I'm giving it energy. If I push in the opposite direction that it's going, I'm taking energy out. Negative work. Work is measured in joules or Newton meters. Power is work over time. Work is change in energy. Same thing. Power is measured in watts or joules per second. Another important thing that might come up, the physics definition of energy is ability to do work. It's kind of weird, but that is literally the definition of what energy is your ability to do work. Change in energy is equal to your work. We've got this. Again, I prefer the MGH. I don't know how you guys think about it. Your equation sheet will talk about the change in height equals the change in energy. Typically, you're going to be using things that are on Earth. So you're going to be comparing, okay, zero energy to wherever your height is. Well, that's just height. So MGH. Kinetic energy, 1/2 mv squared. Notice, which variable has a bigger impact on your kinetic energy? Mass or velocity? Look at the equation. This wasn't a trick question. Kinetic energy. Does the mass have more impact on the energy, or does the velocity? No.
Okay.
Right? This is a number. This is a number squared. If I change this number, and then I have to square it, I'm amplifying that change. If you double V, what's 2 squared? 4. Your total value goes up by 4, not just 2. That's just important to recognize from the equation itself. Potential energy of a spring, that's also 1/2 kx squared. K is the stiffness of the spring. X is your position. This talks about, again, universal potential energy. It's big G. Again, it's negative because it's the amount of energy that you're losing. It's a little weird, it's a little backwards, just so you know why that answer is a negative number. And we talked about those other things. Any big questions about energy? The main points, we got to know kinetic energy, 1/2 mv squared. We need to know potential energy, MGH. You sort of need to know universal potential energy and spring energy. Those will not be super common, but they might bring them up. And work, force times distance, is how much your energy changes. Those are kind of the big things from the energy unit. Any other big questions overall? Okay. I don't know what I edited, but okay. Do you want to have just time to work on either an FRQ or your homework? Do you want to take timed, another FRQ where I time you? Or do you want me to just give you this for you to work on your own? Or do you want us to do the FRQ together? Want to go through it together?
Yes.
Okay. So that's the last thing that I have. Again, just like we've been doing, your guys' homework, I want you to just pick 10 questions from the Unit 4 workbook. Again, I want you to try it, do your best, and then grade yourself. And then, okay, I got to pull it up for you to see. So, again, this question is from the 2017 FRQ. So this was a literal AP question, FRQ question on the 2017 exam. And it's related to energy. Okay, so I'm going to pull up the screen. I want us to think about this together. And I'd really like you to follow along with me. This one works? Yeah. Okay. Does everybody see that? Okay, you got a physics class. You want a low friction slide that's going to end up launching a block. You got two teams that make two different slides. They use identical blocks in both cases. So the size is the same, the mass is the same. Both slides start from the same height, D, above the table. Team 2's table is lower. You notice this? This table is a little bit lower than the Team 1's table. However, the total height above the table is the same. It's just they're shifted down a little bit. Compensate for the lower table, the team constructs at the very end of the slide a rise. This one dips back up so that the block leaves the slide horizontally at the same height H above the actual floor. So that's the first thing going on reading this question, figuring out what's going on. Part A is saying, okay, both the blocks are released from rest at the top of their slides.
Wait.
Yes?
Does low friction mean low friction?
Well, I think you could assume that it's no friction, or acknowledge that the impact of friction is really minimal, and the slide themselves, both slides are low friction. It's not like this one's carpet, massive friction, and that one's like plastic. So friction, you kind of realize it's low, kind of negligible, but it's the same for both. Do the blocks 1 and block 2 land the same distance from their table? So this block's going to leave the table and go like this. This block is going to leave and go like this. It's asking, they're identical tables, they're different heights and different ramps. Is this distance the same as this distance? Are they the same? Are they different? Why or why not?
No.
Why do we say that?
Because the total height difference is lower on this one.
Plus, yeah.
Because when it goes back up, it slows
They
down.
do have the same ending height, though, don't
No.
Ending
Yeah, but there's no friction.
Much higher velocity than two.
That little
because two has
area
to go back up.
underneath
Yeah, but
doesn't
isn't
matter.
the table
You
two
gain,
slow down
you gain
significantly
speed
since
and
it's like
lose the same amount of speed.
since you using the friction going uphill a little bit, right there?
It's kind of a tricky question, actually.
That table looks taller than
I think
This one is.
Yeah.
It is.
So
This height is bigger than this height.
No, it's not.
No, it's
Oh, no, you're right. It's not. The tables are different, but this lip
yeah.
makes this height the exact same.
Which means, but because of that lip,
It's gonna
you
slow down.
gain speed and then you lose the same amount of speed going back up. And so it's as if you go the same distance, which means that the distance that it goes down in the second one is less. So it will gain less speed.
Again, I don't want to tell you right or wrong. I want us to come together. Eventually, I'll tell you.
No, it's not.
This question actually combines energy with kinematics. Remember motion?
Yeah.
One thing I want to point out, if these tables, if they're being launched from the same height above the ground, are either of the blocks in the air longer than the other?
No.
No. As soon as they leave the blocks, or the table, the ramp, gravity's going to pull them down at the same rate. They will hit the ground at the same time.
Right.
At least from the time of release.
So they're going in different
So neither block is getting more hang time to cover more distance. So it's really going to boil down to which ramp has a larger exit velocity.
Yeah.
If I launch hop faster, I cover more ground as I fall on the ground, and then I measure that.
Yeah.
So then the question becomes, wait a minute, which ramp, if any, has a higher exit velocity? Okay, think about energy. Could I find any way to figure out the kinetic energy leaving the ramp? How do I know how much kinetic energy is right here and right here?
Through science.
Where does the kinetic energy come from as it leaves this ramp?
the distance.
Here. Okay, so let's assume this is 0. The potential energy equals mgh. Mass of the block is something. Gravity is 9.8. The height, and this is where it gets tricky.
But the height's the same.
Is this your height, or are you going to measure off of the absolute ground?
No, measured value is the height because the tables are different.
Trying to think if it wouldn't matter.
Wouldn't it just be the track, not really the table? Because you already
Because the
said
table doesn't
that
matter
the
because
track-
they leave at the same height. So we're finding the kinetic energy. The table doesn't matter.
The table doesn't really matter. You already said earlier that it's the same.
So we don't. It doesn't matter how high off the ground they are, because they leave at the same point, and so all we care about now is the exit velocity, and so then the table doesn't matter.
Yeah, okay, so I think it wouldn't matter if you're measuring starting height to exit height.
Right.
Or if you measure starting height minus exit height here. So what we can do is look at, okay, starting height on the table to exit height. It moves down a distance of d. So this distance I'm going to put as d.
So D is the same distance.
Are you sure?
No, it's not.
You said it at the start it was.
The ramp to table. But this has a lip that brings it back up.
Which means that it loses.
So
the
this
same
height
amount of
is the
energy.
same.
Yeah.
So over here, I got to do my equation. UG equals mgh. Well, m, it's the identical block. G is gravity. What is the height difference from here to here?
D minus
A little bit.
H minus H table 1. That's where the table height matters.
D minus,
The height minus the table, or the difference in the tables. So table 1 minus table 2.
yeah, which doesn't tell us, so let's call it x. Some small distance.
So that's the only thing that matters, because you end up gaining less speed because it is different height. lower hang.
What was the question asking us?
Do they land the same distance?
Yeah.
No, because it's less.
So right here, this potential energy is how much energy I have to completely convert into kinetic energy. Which of these numbers is going to be bigger?
The first
Do you guys see that? D is bigger than D minus something. This scenario has more potential energy to convert into kinetic. Again, they launch from the same height off the ground. They're in the air at the same time. So whichever one's faster can cover more distance. This one covers more distance. So then the answer, again, do they have the same distance? The answer is no. You would get 1 point for attempting conservation of energy. So you would have had to say, basically, UG equals 1/2 mv squared. Then you do the same thing, equals 1/2 mv squared. If you write that down, that's conservation of energy. You would get a point. When I'm grading yours, I would give you a point for, oh, yep, they talked about conservation of energy. Then you could either do the math or state this has higher launch velocity. You would get a point for that. Or you could do the equations and see V is bigger in scenario 1 than 2. You'd get another point for saying the time is the same. Remember, that was one of the first things we said. If they leave at the same height from the ground, their hang time is the same. That's where you get the 3 points. Notice, you do not get a point for saying no. If you just checked no and didn't do anything, you don't get any points. Right? It asked you to justify your answer. That's what it asked you to do. It didn't ask you to answer. It asked you to justify your answer. Right? So you have to be careful. Some of the questions, if you could have thought through that all in your head, but it asked you to justify, you're like, oh, I got to write it down. If it asks you to just answer the question, just put your answer down. You don't even have to do work if you don't want to. However, you could get partial credit if your justification was right, or 2 parts of it was right, but the answer was wrong. You could guess incorrectly and still get, say, 2 points for maybe the first 2 parts that you did correctly.
So, like, obviously I wouldn't do this, but like, if I knew the answer was no, justified my answer as saying no, but put yes.
If the wrong answer is selected, you could get partial credit. If you give correct justification, you have to come to the right conclusion.
That's true.
You can't twist physics to make it be whatever you want.
That's true.
It's a good hypothetical.
What if what you're trying to say was wrong, but you got the answer right?
Like you said, no.
So you had bad justification, but somehow got the right answer?
Yeah.
I don't think you would get points, because your 3 points come from the points of justification. If you have those incorrect, you're not thinking about the question right at all. Even if you randomly guessed correctly, all your reasoning is wrong. That doesn't cut it in science. We don't do research and get the right answer with garbage data or faulty reasoning. That's not what scientists do. So that's why they give points for justification. Okay, so let's look at part B. Same thing, but the shapes are different. Right? So we're kind of the same basic setup, but we need to acknowledge, okay, same heights above the tables and exact same heights above the ground. The only difference between these two is the shape. One's a slope, one curves up, then dips down. So the question's focusing on, okay, they're both released from rest at the same time. Which block lands further from the respective table? This is the same mindset as the first part of the question.
friction's in play.
Yes, but it's identical for both of them. It's a good question. And it's also low friction, which you could say, assume negligible friction. So again, which one lands further away?
T1.
Huh?
T1.
We sure?
I say
T1 land. Oh, all right, this is a different.
We're on part B. We're on a new question, new ramps.
two.
We gotta have reasoning. We can't guess blindly.
Because
I say two because
Actually, this says briefly explain your reasoning without manipulating equations. I don't want math and algebra showing me it. It's asking you, give me a conceptual reason. Okay, let's go back. How do each of these blocks get the energy to launch?
Gravity.
Gravity.
Gravity is this. It's the same distance.
mgd above the table. mgd above the table.
They're exactly the same.
They each have the exact same starting energy. So what does that mean about their release energy?
It's the same.
It's the same.
So they move the same.
So they move the same speed from the same height. They're in the air at the same time. So which one launches further?
90.
Bingo. Briefly explain without using equations. What would you paraphrase this thought process that we did?
Gravity is the only thing moving. It's the same distance.
Say that again?
Gravity is the only thing accelerating it, and it accelerates for the same distance.
Well, this distance might be different than this distance.
It's the same y.
The same what?
It's the same y distance.
Okay.
Change in y.
Can you simplify that? What is
Same
this?
equation. Their potential energy.
You have to use words, not equations. What'd you say?
Their potential energy is the same.
Yeah.
Oh.
This was calculating potential energy. I don't get to use the equation. Just use what it is. They both have the same starting potential energy. All that potential energy is converted to kinetic energy in both. So that means they have the same exit velocity. They're the same height above the ground. So their launches are identical at this point. Because it's only asking about the distance. So you would verbally describe that. Now here's a tricky one. The second part of the question, we guessed again. Second part of the question is asking us about time. Which block hits the floor first?
90. Again, because of gravity.
And it's again, no equations, but verbally described. This one is tricky.
Table's the same height. Gravity accelerates everything at the same speed.
Does it?
The blocks are the same mass.
Do I go as fast on this gentle hill as I do a steep hill?
But you're steeper. You're steeper at the after that.
True. But if they released at the same time, this guy's going to move real quick, this guy's going to be slow.
And then he slows down.
This guy's going to keep going fast, he's going to speed up. Again, this isn't considering time. Which ramp is the block going faster for a longer time period? Huh? Right? So, okay, think about it this way. This one, it's going to pick up speed really quick, and then it coasts at a high speed and then leaves.
Right.
It accelerates, picks up its speed very quickly. Right? This one,
Because no.
dilly-dally, dilly-dally. Oh, then it's picking up speed, then it's picking up speed. Look at the coasting length. Well, they kind of look the same, but it's irrelevant because this is a matter of time. Imagine, for argument's sake, that you had a ramp that looks like this. This is the maximum possible acceleration. It's pure free fall, and then it shoots you sideways. You're flying. Yeah, but you're going way faster for longer periods of time.
Right.
You're going to cover your distance much quicker.
Okay.
Right?
Mm-hmm.
So imagine I have another ramp, right? I'm dilly-dallying, I'm kind of picking up speed, then I accelerate. The whole time that this block is meandering and dinking around, this guy's already sped up and already launched off the table. So if it's just a matter of time, the faster you can speed up, the more distance you cover in a certain amount of time, you're going to finish the race faster. Right? When you drag race, you want to go as fast as possible, as quick as possible. That's why you stomp on the gas. If you just sit here and casually, like pick up speed slowly, the other guy's going to fly by you and finish the race before you even get to 20 miles an hour. That's the basic comparison that's going on here. This ramp increases its speed much faster. If you're going faster, you cover more distance just like that. So you will finish the race. So which one hits the floor first? That is a really tricky one. A lot of students would get that question wrong. It's really hard. That's a question that part would really set apart. Okay, who are the 2, 3 students? Who are the 3 or 4 or 5? This is really testing your understanding of physics, how energy and motion come into play. So again, correct answer would be block 1. You get a point for saying the average speed is higher in team 1. On average, at any moment in time, you're moving faster in the first ramp. Or you could say team 1 gets maximum speed much quicker. So it's going to complete the race quicker. Second, why the average speed is higher. What would the reason be? Why does this one pick up speed faster or have a higher average speed? Why?
Say that again?
Why is this table having a higher average speed? Or why does this one reach maximum speed quicker than this ramp?
Is that the we were talking about like with the cars about like that one slowly accelerates while that one just like
Yes. This
Right.
unleashes the speed
Yeah.
and then lets it go.
Yeah.
This one, diddles around, whatever, and then eventually gets up to maximum speed. Well, if it's a race, you want to go as fast as you can, as fast as possible. You really would want to connect it to the energy. This ramp releases its potential energy faster than this one. The energy release is the same. They both have the same starting energy. This one converts it to kinetic energy much faster than this one does. Alright, so just in time. Was this helpful doing it together?
Yes.
Okay, because I want to keep us practicing on your own, challenging yourself, because it's just going to be you on the test. But this is also good to get us learning of how would I solve this problem? I don't know. Working through it together. Please, Brody, I had you remind me, you guys should have seen the email. You guys know where the mock exam is?
In the library?
It's A169.
That's the room across from the tent.
Yeah, if you go and hit the office, if you go to the back side of the office, that's A169. I hope everyone's here tomorrow. I really want you guys to please take advantage of being here for that mock exam. Sure, it's going to be painful, but it's going to be a great experience and practice with no pressure. You're going to get a trial run, see how you do, and then we're going to learn from your mistakes. I'm going to grade them so then you'll get feedback.
Is it after first lunch?
Yes, you guys are going to first lunch, and then right after that, go to room 160, A169. Yes. It'll be good. I know it's...
Wait, so I was not paying attention. Where are we going?
Sounds like a personal problem. A169.
A160.
On the other side of the office. You guys...
Office.
Huh?
Right across from the attendant's office.
Right.